Remind you about these transformer expressions here. And there's some nice descriptions of this in the textbook, but I just want to review really quickly how it works. Transformer, two coils of wire, linked together not by an electrical connection, but by a magnetic connection of a piece of iron core. So I take first the primary coil of wire, it's wrapped around this chunk of iron, and I connect it to an AC current. Why does the current have to be AC for a transformer? Because it's changing flux that makes it happen. And if it's DC, you get a constant current. Do you get a changing flux? No. So it's got to be AC. So connect that to an AC source. I get a flux in here, and it goes one way, and then it goes the other way. All that flux stays inside this iron core because the iron is very strongly magnetized. And then I get a flux in the second coil called the secondary. And then the changing flux inside here induces a voltage in the secondary coil. Okay? Now there's two relationships which we have for transformers. And I want to look at the first one. And it says this, V2 RMS. And the RMS, root mean square, that's an average. Why that is what it is described in chapter 26. Go ahead and take a look at that. And I'm going to leave the RMS off. It's just, basically, it's a way of computing an average. So I get V2, the voltage on the secondary, is equal to the number of turns on the secondary divided by the number of turns on the primary. So the number of turns in the coil times V1. So if I have a transformer that has a lot more turns of wire on the secondary than it does on the primary, if N2 is bigger than N1, that's called a step-up transformer. That makes the voltage bigger. First off, I want to look at the current. Now, the changing flux being the same in both loops gives us this voltage relationship, and you can look in the textbook to see how that works. But if I have a changing current, if I have an AC circuit, voltage changes in the transformer, the current changes as well, and it looks like this. The current in the secondary is N1 over N2 times I1. It's opposite the voltage relationship. So if I increase the voltage, what happens to the current? Decreases. And that makes sense, because the power has to be the same. The product of the voltage times the current in the primary, which is the power in the primary, has to be equal to the power in the secondary. Okay? Let's look at an example of that. You have many devices in your house that look like this, that you stick into wall outlets to run electronic devices. Because our electricity is AC, you can easily convert the voltage from one voltage to another using a transformer. This device has at its heart a transformer, and it tells us what the input is. It's 120 volts AC. Why? That's what's coming out of the wall. And it tells us the output. The output is 9 volts and 1 amp, and it's designed to run at that. It's going to provide 9 volts AC at 1 amp, okay? And typically, electronic devices are designed to run at lower voltages than 120 volts. And so the first stage in them is the power pack. So if you have any kind of electronic devices, anything which needs a charger, you have something like this, and it's a transformer. The voltage is going to decrease, okay? The voltage decreases here because it goes from 120 down to 9. That's more typical. That's more typical. But let's take a look at this. Question 1, what is the power output? Question 2, how many turns of wire on the secondary? Question 3, what are the voltage and the current in the primary? Here's what we'll do. First off, I want to look at the power. And I'm looking for the power, output power, and that means in the secondary. Okay, I'm going to draw a circuit here. Drawing pictures, still a good thing. I'm just drawing a transformer slightly differently. It's this stylized version of a transformer. And I take this device and I hook it up to something in order to make it run. And so I'm hooking it up to something represented by a resistor here. So this is my 120 volts out of my wall outlet. Goes through a transformer, comes out at 9 volts. And so I have 9 volts in this secondary coil. Sends a current around this secondary coil. And then puts a current through this load, which I'm representing here just as a resistor. Okay? And we're told under normal circumstances the current is 1.0 amps. And actually it goes one way and it goes the other way. It's an AC current. We have 400 turns of wire on the primary transformer, and so that's N1 here. The question is asked about N2, But the first thing we're asked about is the power, and we want to know the output power. Well, the output power is the secondary. When I take this transformer and I hook it up to something, how much power does it provide? Well, power is the product of what two quantities? Current and voltage. So it's just V2 times I2. I know V2, that's 9 volts. And I2, 1 amp. And so I end up with 9 watts. 9 watts is the power on the secondary, or the output power. Okay, I'm going to ask you a question, and we're going to use this at the end of the problem as a check on our work. What's the input power to the transformer? 9 watts. Input power, output power is the same. The transformer changes the voltage, it changes the current, but it can't change the power. That's the whole conservation of energy thing that we talked about. Oh yes. So input power, output power, got to be the same. We use that as a check on our work. But next stage, how many turns of wire on the secondary? Well, for that, we can use our voltage equation, which is this. V2 is equal to N2 divided by N1 times V1. What's V1, the voltage on the primary? 120 volts? I know N1, which is 400 turns. V2, voltage on the secondary? 9 volts. So I have everything in this expression except for N2, the number of turns on the secondary. Heavens to Betsy, that's what I want to solve for. That was handy. So if I solve for N2, is it going to be bigger or smaller than 400? Smaller. It's a step-down transformer, and so it's got fewer turns of wire on the secondary. If we solve for this, I get 30 turns of wire. And it's quite a big reduction in the number of turns because it's quite a big reduction in the voltage. What are the voltage and current in the primary? That's the next piece that we want to solve. And I'm going to do this. Oh, I know the voltage in the primary. That's just a rated value. It's 120 volts. How about the current in the primary? Well, I can use my current equation for that. The current in the primary, if we use our transformer relationship, is equal to N2 divided by N1 times the current in the secondary. What's the number of turns in the secondary? 30. Number of turns in the primary, 400. Current in the secondary, 1 amp. So if I solve for that, I get 0.075 amps is what I get for that. And that makes sense. So the primary, high voltage, low current, step it up to the and then it goes to the secondary, which has lower voltage and higher current. Now if I took the transformer and reversed it, so it had more turns on the secondary than the primary, what happens to the voltage? Increases. What happens to the current? Decreases. Okay. And this is a crucial thing.